In this video lesson, we are going to take a look at stoichiometry again, but this time specifically using some of the formulas that we've used with solutions. Okay. In the past, we looked at pure substances, where we took the masses of those pure substances, whether they were a solid, liquid, or maybe even a gas, and we converted the masses into moles using our formula mass divided by molar mass, which required us to take the mass and divide by the molar mass. So if we were dividing, going down the table, we would have divided. If we went up the table, we would have been determining the mass from the moles, okay, by multiplying. We would have done that for any of the pure substances, solids, liquids, or possibly gases. But in this case, when we're looking at solutions, we're dealing with a mixture. And with mixtures, we use concentration to determine the number of moles. Okay. We'll also see in the next unit, when we briefly look at gases, there will be another formula that will allow us to determine the number of moles, especially when we have some other quantities other than mass, such as the pressure, volume, and the temperature of the gas, all related together in something called the ideal gas law. Okay, so pressure, volume. Here we've got our moles. And we rearrange it if we want the moles, and then rearrange it differently if we wanted one of the other quantities there. We get the temperature here. And the temperature is going to be in a different unit when we're talking about gases called Kelvin, so we'll be looking at that. And then there will be a constant called the ideal gas constant. That helps us relate all these quantities. Okay? But with solutions, like I said, we're going to use our formula moles equals concentration times volume, okay, where the concentration's in moles per liter, the volume's in liters, and that's going to give us our moles. Okay? We may be required to find out the volume of something, okay, or the concentration, so we may want to use that little formula triangle there, where we've got moles is equal to the concentration times the volume. We may also be given just a regular concentration, either whether it's in weight per volume, okay, or weight per weight, where in this case, our concentration would be mass divided by volume. We may have to rearrange it to get the mass. Okay? And here the concentration would be in grams per milliliter and the volume in milliliters. Okay? So that's kind of the framework we're looking at, but it's the same kind of idea. With any stoichiometry, we need a balanced chemical equation. We have to know what our starting materials are and quantities. Figure out the moles, allow the moles to be used and the balanced equation, the coefficients of the balanced equation to be used with some ratio and proportional reasoning to be able to determine the other quantity of the substance, whether it's another reactant or a product. Okay, and then once we find out the moles of the desired substance, we can convert it into mass or volume, depending on the needs of the question. Okay, so we'll take a look at a couple examples there. So first one here. So first one says, if we have 500 milliliters of 0.1 mole per liter, 0.7 mole per liter solution of HCl that reacts with some zinc metal. Here are my questions. What mass of zinc chlorides produce? Okay, that's this thing here. And what mass of zinc metal is needed? Okay, so the problem gives me some information. Okay, so this is what I'm given here. I've got a volume, and it looks like a concentration based on the units for HCl. So I'm going to have some information about HCl here. And then I have two questions. I want the mass of the zinc chloride, and I want the mass of the metal. I want the mass of one of the reactants and mass of a product. Okay? So just as in the other questions that we dealt with stoichiometry, I like to organize my information. Okay, so the concentration is 0.700 moles per liter. I've got a volume, which is 500 milliliters. And now I need to find the moles. Okay, so there's a couple of little differences here. First of all, I got to make sure these units match. And they don't right now. So this is in milliliters. I need it in liters. Okay, so there is 1,000 milliliters in 1 liter. So if I'm going from 1,000 to 1, I'm going to be dividing by this factor. So I'm going to divide by 1,000 to get my liters. So it's 0.5 liters there. So that's one thing that I need to do. The other thing to do is I'm not going to blindly just divide or multiply like I did with these formulas. This was just getting us started, getting used to these formulas. Really, because we're finding moles, we need to divide, and because we're finding mass, we needed to multiply when we went up the table. This is different here. We're applying an actual formula to determine the moles. Okay? And I know for solutions, the formula is a little different. Moles is equal to concentration times the volume. So I need to multiply for these guys. So I usually write the formula down, put my numbers in, 0.7 moles per liter, 0.5 liters, multiply them through, and I get 0.35 moles. So that's the starting point that I need to achieve for the stoichiometry question. Okay, so that's taking my given information and getting us started. Now what I need to do is figure out how many moles of zinc chloride are produced and how many moles of zinc is needed, zinc solid that's needed. Okay, and remember, I'm using the coefficients here to help me out. So I'm going to move from the hydrochloric acid to the zinc. There's a coefficient of 2 there and a 1 there, so it's 2 to 1. Okay, and so if I'm going from a large to a smaller, I'm going to have to divide, and the factors fairly easily. I'm just dividing by 2. So my moles here is 0.35 multiplied by, or divided by 2, which is 0.175 moles. Okay, so this is that ratio or proportional reasoning step that I need to do. Might as well, I know I'm going to figure out the same thing for zinc metal. So I've got to go from the moles of HCl to the zinc. And again, I'm going from 2 to 1. I want you to notice the direction of my arrow kind of shows me the way I'm changing these numbers. It's 2 down to 1. So again, I am dividing by 2. So I'm doing the exact same thing here. It's the same number of moles of zinc as there is zinc chloride. And that kind of matches what the coefficients say in the reaction. Okay, 0.175 is the number of moles of zinc that I have that are needed for this reaction. Okay, so I got both my moles. So the last step is I'm finding the mass of both of these. Now, just like I did with solids or pure substances in this case, I am applying this formula. So I need the moles times the molar mass. I am going to multiply to get up the table here. So I do need their molar mass. So zinc is, I believe it is 65.39 grams per mole. And for the zinc chloride, I just have to add them together. There's one zinc, so 65.39 plus 2 times 35.45 on the periodic table, so 136.29 grams per mole. Okay, and because I'm finding mass, I am multiplying this time. So I'll pretty easily be able to find out the moles here. Okay, so moles wise, or mass, I think. So, so my molar mass is 136.29 grams per mole. I need to multiply that by the moles, and that gives me my mass, 23.85 grams. And that's how much zinc chloride I'm expecting to produce. Also, I have my moles for zinc that I needed, multiplied by 65.39, and that tells me I have to have at least 11.4 grams of zinc for this to react. Okay, let's take a look at example 2. A little bit harder. This one's a little different. So in this case, let's just take a look. It says I've got half mole per liter calcium chloride and 1 mole per liter potassium carbonate that are provided. What volume of each solution is needed so that I can produce 10 grams of calcium carbonate. Okay, so again, I've got some given information. So this is given to me, and actually it seems to be the complete bit of information here. Okay, so 10 grams of the carbonate, calcium carbonate. I also am given some concentrations of some reactants. Okay, so I can take that into account too. So here's my concentration for the calcium carbonate, 0.500 moles per liter. And here I've got 1 mole per liter of the potassium carbonate solutions. Okay, but it's asking for the volumes that I need. So even though I have some information about these, I'm still lacking something for the volumes. So as a result, this is the question. The question is, how much of each solution do I need? Okay? So just like in the last question, I'm going to have to get to moles. Is there something here that gives me a complete bit of information? Well, this does. Because the calcium carbonate, I can easily find its molar mass. Okay, just using the periodic table. Calcium is 40.08, carbonate 1.01, carbon and then 3 oxygens at 16 gives me 100.09 grams per mole. Okay, remember the formula for moles is mass divided by molar mass, so I am going to divide in this case. Divide those two, so 10 divide by my molar mass gives me a mole amount. Okay. And then finally, if that's my mole amount, I'm just going to double check that everything's balanced. Everything's balanced, so it's 1 to 1 in each case. That makes things a lot simpler. So I'm just going to leave a little bit of space here. So the moles, because it's 1 to 1, I'm not changing the number of moles. It happens to be the same ratio. So the number of moles of potassium carbonate that's needed matches the number of moles of calcium carbonate that I'm going to use, or I'm going to produce, and also the moles of calcium chloride that are needed. Also matches the number of moles of calcium carbonate that's produced. Okay, so I've got my moles, I've got my concentration. I'm going to have to rely a little bit on my formula triangle, and I see that if I want the volume, it's going to be moles divided by concentration. Okay, so this is the part that I'm going to need. So I've got my moles. I'm going to divide by my concentration, and then I will get the volume. And it'll be in liters. Okay, 0.1998 liters of calcium carbonate is required. And then the same idea here. This one's a little easier. 0.0999 liters of potassium carbonate is required at that concentration. So in the end, therefore, and I would multiply this by 1,000 just to get milliliters. 199.8 mils of calcium carbonate at a half mole per liter. And same thing, multiply that by 1,000. 99.9 ml of potassium carbonate at 1 mole per liter are required to get your 10 grams of calcium carbonate. Okay, so that's it for this lesson. Try these questions. You can apply any of the other things that we do in stoichiometry to these solution stoichiometry questions, limiting reactants, percent yield, all that kind of stuff. The answers are here too. Okay?